Okay, we're going to talk about improper integrals today, and the foundation of improper integrals, first of all, I need to make sure that you remember what the fundamental theorem of calculus is. So here's the definition of the fundamental theorem of calculus that we've covered previously in this class. So remember, if a function is continuous from an interval from a to b, and capital F is the antiderivative of the function f from that interval from a to b, then we can say that the definite integral from a to b of the function is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So that's how we find area under the curve. Yes?
So on one of the tests, number 4, when it was the absolute value of x minus 2, and it asked you the intervals on which it was differentiable, or integrable, in this definition it says that function f only has to be continuous. It doesn't
Correct.
say it has to be differentiable on the interval. So why was the answer A and C and not A, B, and C?
Okay. Let's start out about the fact that then you need to go back to the definition of a derivative. In order to be derivable, you need to have what? Continuity, right? And you cannot have a sharp point. The problem on that test had a sharp point at value 1, I believe. Therefore, you cannot differentiate it. And if you cannot differentiate it, you cannot integrate it. So therefore, you had to split up that problem into two intervals of continuous, continuous intervals from whatever to 1. I don't remember the problem, from 1 to whatever, so that you could integrate. Cool? All right. So here's what's going to happen. So like I said, we're going to solve intervals where one of the limits is going to be to infinity. So there's going to be 3 scenarios. So first of all, let's talk about improper integrals with infinite integration. So what I mean by that is, here's the first example of what you can come up with. Let's pretend that you have a function that is continuous on an interval from some value to infinity. Okay? So we want to find the area between that value and infinity of the given function. Because we cannot do operations, and I hope you remember this, we cannot do operations with infinity, right? We're going to have to go back to the basis of what calculus is. Everything we've done in this class has a limit working in the background. Do you remember that the foundation of integration, of derivatives and everything is limits?
Yes.
So we're going to use limits to solve this out. So what I'm going to do is I'm going to rewrite the initial statement, but instead of saying from a to infinity, I'm going to replace infinity with a b. So I'm going to say the integral from a to b of f of x dx. But because I replaced it with a b, I'm going to have to take the limit as b approaches infinity, because that's what I replaced it with. You with me? Okay. Case 2 is the same thing, but I just flip things. What if instead of going from a number to infinity, I go from negative infinity to a number? Well, the same situation occurs. I need to replace that negative infinity with a variable. So by doing such thing, I replaced it, for example, in this second one with an a. So now I can do from a to b. But I need to find the limit as a approaches negative infinity, because that's what a is equal to, right? That's what I replaced it with. Cool?
These are one-sided limits?
Not necessarily. No.
But then how can you approach infinity from the left?
It's still, so that's where it gets a little tricky. Hold on, give me just a second.
Okay.
What's up, Zach?
Is b an arbitrary number?
Yes, so we're gonna, in which example?
One.
On the first one? Then b is not an arbitrary number. B is infinity.
But I mean, how do you plug it in now?
We're gonna do an example. Okay.
So like, what if it was like some like you going to infinity part, which was like 5x? Could you also do like something in
No, we've talked about that. Then at that moment, you need to do the second fundamental theorem of calculus.
Yeah.
Remember? So with the second fundamental theorem of calculus, the second fundamental theorem of calculus proves that integrals and derivatives are inverses of each other. Cool? All right. Last scenario would be worst case scenario. What if you are going indeed from negative infinity to positive infinity? In other words, think about this. It's like I give you a function and I want to find the area under the curve over its entire domain. Okay? Yes?
For y equals x, would that be 0?
For y equals x with y equals 0. No, it would be divergent. Think about it. Just continue to grow and grow and grow and grow and grow.
Y equals x from negative infinity to
But
infinity.
that would be infinity minus infinity. We cannot do operations with infinity. right? Right? So it'll be divergent. Okay, so what's going to happen is you're going to have to split it up into two integrals. I split it up from negative infinity to c, and then from c to infinity. Now, c will be an arbitrary value. You get to pick whatever value you want. I recommend that you use 0, because 0 is an easy number to deal with, right?
Yep.
And then you just apply the rules from above to finish each one of those
It's easy
limits.
until you divide by it.
There you go. I agree.
What is the second one? Oh, I see, you split up into two integrals.
I just split it up into two integrals. One that goes from negative infinity to an arbitrary value, and then I pick it up from that arbitrary value to infinity. And if you look at this two, they're basically the examples from above, right? And that's technically what it becomes, the examples from above, right? Okay. Right there at the bottom of the page, I wrote that the definite integral converges if the limits exist. So if the limit exists, you should get an answer, right? So like you can get a limit, let's say that the limit is equal to 5, then you would say that it converges, right? Therefore, you can assume that the area under the curve will be 5. But if you don't get a value, you would say that it diverges. Okay? So if you're watching the video, I'm going to go ahead and pause it so that you can catch up, and then when you're ready, just hit play. Alright, so I'm assuming you've already copied down the notes, so we're going to do 3 examples dealing with the 3 rules, obviously one for each one. So let's go ahead and try example number 1. Let's say that we have the integral from 1 to infinity of 4 over x to the 4th power dx. Okay, right away, very obvious this is improper, right? You have an infinity. Before you do any calculus, rewrite it, substitute that infinity with a variable, and rewrite it as a limit. So we're going to rewrite this as what? The limit as what?
B approaches infinity.
So b approaches infinity of the integral from,
A to B.
so 1 to b, because you actually have a value. So 1 to b of 4, and can I make my life easier and rewrite this now as 4x to the negative 4 for when I have to integrate, right? You with me? Now that's the first step. We just rewrote it as a limit. Now that you have it as a limit, you are going to go ahead and apply the fundamental theorem of calculus, which is integrate this thing, right, and then evaluate at b and at 1, right? So if I do such thing, what is the integral of 4x to the negative 4th power? So it's going to be x to the negative 3rd, so 4x to the negative 3rd divided by negative 3, evaluated from where to where? From 1 to b, and I'm still going to have to take the limit of that, agreed? So I'm going to continue to write that. You with me? Yes? Okay, now I'm going to clean this up a little bit so that it makes the math a little easier. So it's going to be the limit as b approaches infinity of, if I rewrite this, isn't that the same thing as negative 4 over 3x cubed? Yes? Now, do you have to show that step? No. I'm just trying to make sure that for those of you watching and right now during notes, you understand what's happening. Okay? What do I do now? So fundamental theorem of calculus, so do what? So plug in b for x, alright? So then this becomes the limit as b approaches infinity of, if I first plug in b, I get negative 4 over 3b cubed. And then what do I do after that?
And then subtract.
So it's minus negative 4 over 3, 1 cubed, right? Yes? So, you're with me? Like,
The answer is 1/3.
so hold on. Yes. So here's what happens. Here's where I'm at then. The limit as b approaches infinity of, well, I can reduce that, so it's going to be negative 4 over 3b to the 3rd, and this becomes plus 4/3. Now, I'm going to go back, and I'm going to use some of the properties of limits just so that you don't forget them. Do you remember that I can split this limit into two limits? I can split it up as the limit as b approaches infinity of negative 4 over 3b cubed plus the limit as b approaches infinity of 4/3. Do you guys remember those properties? Sweet. Okay, let's solve the easy one. What happens as you approach infinity of 4/3? It's just going to be 4/3, right? Okay, now here's the one that we struggle a little bit, so hopefully you remember your how to solve limits. If I plug in infinity here, that means that this number just continues to get larger and larger and larger, the denominator, right? A number over something that's larger and larger and larger approaches what? 0. So what's the answer?
4/3.
The fact that you have an answer tells you what?
It's convergent.
This converges. So here's what I would say. I'm going to go ahead and finish this up. Therefore, the integral from 1 to infinity of 4 over x to the 4th dx converges, and it's equal to what? 4/3, right?
Is that how we phrase it in that one too?
Yep. No, because we brought the limit to solve it. You with me? Like I rewrote it as the beginning problem, right? The very beginning. So that thing converges, and it converges to 4/3. So something that you would answer, as long as all this is present there, like it's equal to 4/3, or you would say converges to 4/3, or something along those lines, that would be correct. You with me? Okay. Question. Well, let's think about this for a moment. How would this look like graphically? Well, let's kind of give ourselves a sketch. Okay. How do I find this thing has asymptotes? Yes? It has an asymptote, and it has a vertical asymptote where? At x equals 0, because you set the denominator equal to 0. So I have an asymptote there. Do I have horizontal asymptotes? Where? At 0. Why?
Because the bottom is larger than the top.
Good. Larger degree. So bigger on bottom means that you have a asymptote of y equals 0. Now, so if we start plugging in numbers, like for example, if I plug in a 1, I get 4, right? So it's like right there. So then based on that, I'm like, okay, that's all I need. This thing is going like this, right? Yes? So here's what we just found out. According to what I'm looking for, this is 1. The area between the x-axis until forever going that way is 4/3. Exactly 4/3.
That's crazy.
Okay? That won't always be the case. Example number 2.
Man, using Leibniz.
I want you to try this one on your own. It's very similar to the first one, but heads up, you are going to get divergence. But make sure that you can get there.
So
Okay?
we'll be in Dauntless.
Example number 2. Let's do the integral from 1 to infinity of 2x to the negative 1/5 power dx.
The 5th root. Oh, the negative.
Okay? So I'm going to go ahead and pause the video if you're watching this. Try this problem, and when you're ready to check your answer, just go ahead and hit play. Alright, I'm assuming you've already tried this problem, so let's kind of go over it relatively quickly. So the first step we did is we substituted infinity here with a b and wrote it as the limit as b approaches infinity. Then we're going to actually integrate this thing, so we got to add 1 to the negative 1/5, which becomes a 4/5, so we got to divide by that, which becomes 5/2. We got to apply the fundamental theorem of calculus, so we got to go from 1 to b. And doing so would then become the limit as b approaches infinity of 5/2 times b to the 4/5 power minus, well, if we plug in 1, it's just going to be 5/2. Right? Now, the limit as you approach infinity of this, well, infinity to any power is just going to get bigger, right? So this is just some type of infinity. Minus 5/2, taking away 5/2 from infinity, it's not going to do anything to it, giving you infinity, therefore diverges. Cool? Alright. Then let's go ahead and move on to example number 3.
So is the answer you're looking for diverges or converges, or is the answer you're looking for?
If it converges, they're going to look for the number that it converges to.
But if it's diverges,
If it's divergence, then you just say diverges.
it's either infinity or negative infinity.
You don't say that, you just say diverges.
Diverges.
Yep. Okay, example number 3. Let's make this more fun. Let's do the integral between negative infinity
Positive
and
infinity.
positive infinity.
Oh, God.
And let's make the integration fun too. Why not? 4 over 36 plus x squared dx.
Oh my God, this is the inverse trig, yeah.
This is inverse trig. Which one specifically?
Arctangent.
Arctangent.
It's good that we
Cool.
recognize it.
Alright, but before you apply any of your integration rules, first rewrite this in terms of limits before you do anything else. Okay, so first, what I'm going to do, I'm going to make my life easy. I'm going to rewrite this as the integral from negative infinity to 0
0 plus the limit
of 4 over 36 plus x squared dx plus what?
plus the integral from 0 to infinity.
From 0 to infinity of 4 over 36 plus x squared dx. Why choose 0?
Because it's just a nice number.
It's going to be nice because you know how to take the arctangent of 0, hopefully. Right? Hopefully.
Oh,
We'll find out. But anyways, we'll get there here in just a minute. So let's first tackle this first one. How would we rewrite this first part as a limit?
As the limit of a approaches negative to infinity.
The limit as a approaches negative infinity
the
of
integral
from a to 0
of 4 over 3x plus x.
over
36
36 plus x squared dx plus the second one become the limit as what?
b approaches negative
B approaches positive infinity
of the integral of 4 or of the integral
0
from 0 to b
0 to b of 4 over
x
36 plus x squared dx. Are we okay with that? We have not done any calculus yet. We just rewrote the problem. Yes? Okay, then take one at a time. So we gotta integrate this. Okay, so for sure I still need to write the word limit, right? So the limit as a approaches negative infinity of, okay, here's where it gets interesting. So do you remember the rule for arctangent?
1 over a arctangent u.
Good, so 1 over a, but I'm going to pull out the 4, right? So it's 4 times 1 over a. So what's a? So it'll be 1/6, so it's over 6, right? Arctangent of x over 6, and this is going to be evaluated from a to 0. And luckily for you, it's the exact same thing on the other one, right? So plus the limit,
Isn't it always going to be the exact?
exactly, it's always going to be exact same thing.
Then how is that luck? That's just how it works.
Well, it's lucky that you don't have to do another integration. That's what I'm saying, right? So it's, I'm going to go ahead and reduce that. 4/6 is 2/3, right? So 2/3 arctangent of x over 6 from 0 to b. Yes? Okay, so here's where we're at. Now we're going to apply the fundamental, right? Fundamental theorem. So we got to plug in on this very first one. We got to plug in 0 first, right? Okay. So 0 over 6 is,
0.
okay, what's the arctangent of 0?
0.
0. If you forgot from pre-cal, what this is saying is like, hey, where on the unit circle
Is sine equal to 0?
does tangent equal to 0? And that would be where sine is equal to 0, which is at 0 degrees or 0 radians.
Or negative
So this
pi.
is 0,
Oh,
but we
the-
cannot use
because it's
pi or
first
negative
and fourth
pi
factor.
because when we do inverses, we restrict the domains from negative pi over 2 to positive pi over 2. That's going to come up here in just a second, so I'll re-explain what that means here in just a second. This right here is 0 if we plug in 0. 0 times 4, 6 is still 0, right?
So it's 0.
But minus, right, now I got to plug in the a. So this is going to be the limit as a approaches negative infinity of minus, and I'm going to plug in the a, right? So 2/3 arctangent of a over 6. Agreed? I mean, technically I should have a 0 there, but totally necessary, right? 0 minus, agreed? Okay. Now the other one becomes plus the limit as b approaches infinity, and this time we're going to plug in b first. So by plugging in b, we get 2/3 arctangent of b over 6, and once again, if I plug in 0, I'm just going to get 0. Yes? Okay, so here's where I'm left. I gotta solve this limit. The limit as a approaches negative infinity of negative 2/3 arctangent of a over 6. Okay, so to solve this, I'm going to flip the page so I can show you how you would solve this, because you need to know what this looks like graphically in order to solve this. So I'm going to flip this, and I'm going to show you what you would be hopefully thinking or graphing. Hold on. Let's first talk about the graph of y equals tangent of x. Do you remember what that looks like?
Kind of looks like x cubed.
Kinda, but we have asymptotes. So where is tangent undefined?
Pi over 2, negative.
So at pi over 2, so let's say that that's pi over 2, so you would have an asymptote there, and you would also have an asymptote at negative pi over 2. You guys recall that? Yeah. And then you would have two input numbers, and it looks like that. You remember that from freakout? Yeah. Now, technically this repeats over and over again because tangent is cyclical, but if we want to do an inverse, it has to be able to pass the horizontal line test. And if I do another cycle, I'm not going to pass the horizontal line test. So this is as much of the graph as I can use to have an inverse. And when I do an inverse, x and y switch. So if I want to graph inverse of tangent, that means that instead of having vertical asymptotes, I have horizontal at that exact same location. So this is going to be pi over 2, and this is going to be negative pi over 2. Now, just to make sure you sketch it correctly, like let's pick up, for example, what's the tangent of pi over 4? 1. So that means your x and your y, right? So your x is pi over 4, your y is 1. So if we switch them, it's 1 pi over 4, right? So I'm going to be like, okay, so it's got to be somewhere up here. So that's how I know that this thing goes like that. You with me? Okay. I'm going to use this, and I'm going to go back to what the question was. The question was, what is the limit as b approaches negative infinity of negative 2/3 arctangent of, what was it, b over 6?
Yeah.
Okay. So it's like I'm going to plug in a bigger and bigger number, right?
That's pi over 3. It doesn't matter.
Okay, hold on. Oh, or a, I'm sorry. A. So this is an a, right? Okay. So that just means this is just bigger and bigger negative number, right? So that means I am going bigger and bigger and bigger and bigger. That way. What am I approaching?
Negative pi over 2.
Negative pi over 2. So this right here is negative pi over 2 times negative 2/3.
Pi over 3.
You with me? Yes? And then the other one was plus the limits as b approaches infinity of 2/3 arctangent of b over 6. But this time you're plugging in infinity. So this just gets larger and larger, right? So according to the graph, if this gets larger and larger and larger, I approach. So then that's 2/3 times pi over 2. And I gotta add them. So the negatives go away, the 2's go away, so it's pi over 3 plus pi over 3, which is equal to 2 pi over 3. Therefore, what can we say about the graph?
The integral from negative infinity to infinity
Okay.
of 4 over 36.
So therefore, the integral from negative infinity to positive infinity of 4 over 36 plus x squared dx converges to, what was it, 2 pi over 3?
Yeah.
So converges, right? And we would be done with that. How we doing?
That's so cool.
I'm not impressed. That's funny. So let me kind of graphically, let me just kind of what this looks like.
Oh yeah. I felt like it wasn't happening.
All Are we okay? No?
Why? That was so cool though.
Alright, so we covered the 3 examples there that I wanted to cover as far as like we did, you know, one of them being infinity, and then when it happens to be that both of them are infinity, okay? But that's not the only type of improper integral. Those are very obvious to notice. You're like, oh, that's improper because one of the limits there is infinity, right? So it's improper, I gotta turn it into a limit. But what if it's not that obvious? And that's what we're gonna do now. So what if we deal with something like this? Let me kind of show you where we're going with this. So let's say that you have a graph that looks like there's an asymptote there, and let's say there's an asymptote there, and let's say this thing looks like that, and this one looks like that. And then I want you to integrate and find the area between here. Let's say that that's value of 1, and let's say that this is, what's 2, 3, 4, 5, let's say that's 6, and here.
Oh.
So we have a problem, because when I write this problem, I'm going to have a 1 and a 6 there.
Wait, but that goes against the definition
So,
of an integral.
exactly, so hold on. So at that point, when you see that, you're going to be like, oh, that's not improper, right? It's 1 to 6. But what happens, there's a discontinuity in the middle of the integral. So you cannot integrate that way. You're going to have to manipulate it to make it work. So, hold on. So we're going to separate it. Yes. We need to figure out what that discontinuity is. So first, let's go ahead and write out the rules. And here's what the rules say. So the definition of an improper integral when you have an infinite discontinuity. Infinite discontinuity means an asymptote. Okay. So let's start out with the first one. If the function is continuous from a to b, and notice the way I wrote a to b. What does this mean?
B is like closed.
That means b is not included, which means that this right here is where the asymptote is located. You with me?
Oh, so you can take a limit as something approaches.
Correct. So what's going to happen here is, look, first of all, it's going to be written this way. And you're going to have to realize, for example, on this one, that b is a problem. B is an asymptote. So we're going to have to take care of that. We're going to substitute it with another variable. So I'm going to choose c. But we're going to have to take the limit as that variable right here that we replaced it. So c approaches b, but from the negative side. Why from the negative side?
Wait, on the top.
So from the left side. Why?
Wait, which one is the left one?
Why would I have to find the limit as c approaches b from the left?
Because you can't go from the right because you're trying to find the...
Yeah, it's going
If we go back to this problem, so let's say that here's where you have an asymptote,
Wait,
right?
you put that back.
You with me? And let's say that that right there is the b value. And let's say that this is the a value, and let's say that this is what the graph looks like. You with me? Do you see how you are approaching this value from the left-hand side? You're approaching b from the left. Therefore, we have to find the limit from the left. Okay. Same situation, but now let's talk about what happens if the asymptote is right at the beginning, so at a. Well, it's the exact same thing, but this time you're going to have to approach it from the right-hand side. You with me? Yes, sir. Yeah, it's a C. Yes, C approaches B from the left.
And if the asymptote was in the middle, you would just split up the integral of the two parts and then take those two rules and put them together.
Yes, sir. So I'm getting a little ahead of myself, but yes, that's like the rule number 3, which is like, hey, what happens if the problem is not at the end, but the problem is right in the middle? So then at that point, you're going to have to split it into the integral from the beginning all the way to where the problem is. So C this time is going to be where our asymptote is located. And then do the same thing from that asymptote to the other endpoint. and apply the rules above. Okay? So I'm going to go ahead and pause this video so you can go ahead and copy everything down, and then we'll move on from there. Alright. Okay, so this third one is probably the one that gets a little bit more complicated to comprehend. So what's happening here is, first of all, you're going to have a function that indeed is continuous. Like, notice how we are including both of the values. What this is saying is, like, the problem is not at the endpoints like the first two examples. Like, the problem was here at B, at the endpoint, on the first one, and then it was A at the first endpoint. So what happens here is that, hey, we don't have a problem at the endpoint. We have the problem somewhere in between, so some value C in between. So that means that the asymptote is going to be somewhere in the middle. So what we're going to do, so let me go ahead and kind of sketch what that looks like. So let's go back to this sketch that I had earlier. So let's pretend that there's where your asymptotes are at. But just for the sake of this, what I'm trying to prove here, instead of making that B, let's make that C. You with me? And let's make this over here, let's just pretend that the graph looks like this. Okay? And let's make this value B. So what I'm interested in is I would be interested at from A to B. So at that point, notice how you have an asymptote here in the middle. So what you need to do is, and according to this definition, is, hey, you need to figure out what that value is, what's giving you the problem. So we need to figure out what C is, which for the sake of this, like, there's C, that's what it is, right? So it's like saying, you know what, you're going to have to do an integral from here to here, from A to C. So we're going to do the integral from A to C of the function. And then you're going to do the integral from here to here. You with me? And that's where we got this there, from C to B. Now, I got lazy, but basically, if you look at this, this is the same thing as what? That very first one. So it would become the limit as C approaches B from the negative side from A to C of f of x dx, plus this part right here would become that one. You with me? So you were still using a limit. Okay? Yes, sir.
Then wouldn't there be like 4 variables in this community? Because like the C and that one.
Mm-hmm. It's the same thing, so you're going to have to stay very organized with this. Okay?
No, like when you're going from like 3 to like 1,
Uh-huh.
you use C up there, so then we have to use like C.
No. Let me do an example and I'll show you how to take care of it. Now, the last thing I wanted to make sure I tell you is that if you solve one of the limits and one of the limit diverges, then the entire thing diverges automatically. Okay? Now, I know it's very difficult to try to make sense of some rules without trying a problem. So sometimes just trying a problem is going to clear things out for you. Okay? So let's try out a problem and let's see what happens. Okay? So example number 4 for today. Example number 4. Tell me that thing is recording, please. Is it? Okay, sweet. All right, example number 4. We're going to do an integral, and I want to do one that's going to be very obvious. An integral from 0 to 1 of 1 over the cube root of x dx. Now, let's be honest. Most of us are not going to be looking for improper right away. You know this is improper because that's what we're doing today. But if I just gave you this, you're just going to look at it and like, oh, great, look. There's nothing to tell you right away this is improper, right? As opposed to the very first 3 examples. You knew right away they were improper. Why?
Because it had an infinity.
Because they had an infinity in there. Now, this one's getting a little bit trickier. But once you start working with them, you're going to run into a problem, and that's when you need to say, wait a second. I need to go back and check this. This could be improper. And indeed, it should be improper because according to the graph of this, you should have a vertical asymptote where?
0.
At 0, which happens to be there. So 0 is our problem. Yes, sir?
Why can you not say x to the negative 1/3?
You can.
It still would be
It's the same thing, but it's still not going to work. Okay? So here we go. You ready? So what we have is 0 is a problem, right? So what do we have to do?
So you substitute 0, C,
With some, whatever variable you want. What variable do you want to use? You said C? Okay. The limit of C approaches what? 0 from where? From the right of the integral from where to where? From C to 1 of x to the negative 1/3 dx. Okay. So hopefully you have not forgotten on how to find one-sided limits. Okay? But let's go ahead, we'll take care of that here in just a second. Let's integrate this thing. I'm going to add 1, so that becomes x to the 2/3. And dividing by 2/3 gives me a 3/2, right? And I got to evaluate this from where to where? From C to 1. And I got to take the limit as C approaches 0 from the right-hand side. Yes? So then the limit as C approaches 0 from the right-hand side, if I plug in 1, I get what? 3/2. Minus, if I plug in C, I get 3/2 C to the 2/3 powers. Now, I hope you have not forgotten how to solve limits. What's the first thing you need to try when solving a limit? Plug in. Because if it works, you're done. Right? If it doesn't, we need to try something else. Okay, if I plug in 0, I'm going to plug in 0 into C. 0 to the 2/3 power is, times 3/2 is, so 3/2 minus 0 is, so what can you tell me then?
It converges.
Therefore, converges the integral from 0 to 1 of 1 over the cube root of x dx is equal to 3/2. Okay with that? Questions? Yes, sir. Oh, you just... Okay. Example number 5. We're going to do the integral from negative 1 to 2. And again, let's keep it basic. 1 over x to the 3rd power. Okay. We have a problem,
The third case.
right? Where do we have a problem?
Vertical asymptote is 0.
Vertical asymptote at 0. So you're going to first have to rewrite this as what? The integral from where to where?
The integral from negative 1 to 0.
Negative 1 to 0 of 1 over x to the 3rd dx plus the integral from where to where? 0 to 2 of 1 over x to the 3rd dx. Yes? Now what's the problem here? Yes, C is your asymptote. So in other words, I need to replace 0 with C. So I'm going to say the limit as C approaches 0 from where?
From the left-hand side.
From the left of negative 1 to C of x to the negative 3rd dx plus the limit as C approaches 0 from the right of x to the negative 3rd dx. If you're getting thrown off by how do I know if it's coming from the left or from the right, can anybody kind of see how you can tell shortcut wise?
If C is on the top, then you go from the left. And
Yes.
If C is on the bottom, you go from the right.
Correct. Cool?
Oh, you forgot the integral sign.
Oh, I'm sorry. Thank you. So from C to 2, right? Okay, from there, again, fundamental theorem of calculus. So the limit as C approaches 0 from the left. If I integrate this thing, I'm going to add 1 and divide by negative 2, right? So that becomes negative,
Negative 1/2 x to the negative 2.
so negative 1 over 2x squared, like that,
Yeah.
if I simplify it, right? And I'm going to evaluate that from where to where?
Negative 1 to C.
Negative 1 to C. Plus the limit as C approaches 0 from the right of the same thing, right? So negative 1 over 2x squared, but this time I'm going from c to 2. We okay so far? Okay, now I'm going to go ahead and plug in values. So this becomes the limit as c approaches 0 from the left, from negative 1 over 2c squared, right? Plus 1 over, if I plug in the negative 1 there, I get 2. Correct? Yes? Okay. So that's the first one. Plus the limit as c approaches 0 from the right. And this time I'm going to plug in 2 first, right? So if I plug in 2, 2 squared is 4 times 2 is 8, so it's negative 1/8. Plus 1 over 2 times c squared.
Oh, because you plus because it's negative.
Yeah, minus and the negative will make it into a plus, right? Okay. Well, now we got to answer this. But we have a problem. Because the first thing you should try to do with limits is plug in first. Because if it works, we're good to go, right? But if we plug in 0, we get 1 over 0, and that's not possible. Yes, sir.
So in this case, the direction of the limit doesn't matter because the way even degree at like rational functions work. But like if you had 1 over x to the 4th, it would matter.
It would matter as far as what?
It would matter as far as the limit, right? Because 1 over x squared, it approaches infinity from both sides. But 1 over x cubed, it depends on which side you come from, the limit.
But they both are going to approach some type of infinity. Do you agree? Okay. All right. I know you understand what's happening, so let me make sure I don't lose anyone else and why it is infinity. What's up? Sure. But that's going to give you your horizontals, and we don't care about the horizontals. But that one was to infinity. This one is to 0. Like what happens is we approach 0 from the left. Okay, so stay with me, guys. So here's what's gonna happen. Like the first, like let's say, I could break this up into 4 limits, but I don't want to do that. Like, do you see? Like I can do the limit from here for this one, and then for this one, right? And then for this one, and then for that one. So let's answer the ones that are obvious, which is the constants. That one's just gonna be 1/2, right? And this one's going to be negative 1/8. Now, here is where, again, you should have a relatively good knowledge of what graphs look like. Forget the beginning problem. Here's where you're at. You have this, right? Negative 1 over 2c squared. If you were to graph that, negative 1 over 2c squared, if you were to graph that, just pretend that's an x. Is that okay? So if we pretend that's an x, that means you have an asymptote where? At 0. And you have a horizontal here, right? Now, if you plug in any value, it's going to be negative, right? Do you agree? So this thing is going to look something like that. Yes? You with me? Okay. The limit question was, what happens as you approach 0 from where? From the left. So as I am approaching 0 from the left, I am going to from the left, thank you. From the left, I am approaching negative infinity. So if I go back to the problem, that means that this is negative infinity. Now, adding 1/2 to negative infinity, is that going to do much? No. The moment one of them diverges, don't even bother finishing the problem. The entire thing diverges. So the moment I saw this plus a 1/2, that's infinity, negative infinity. Therefore, the integral between negative 1 and 2 of 1 over x to the 3rd power dx diverges. Cool? If we finished it, you should then realize if I go back to that graph, that's still going to be infinity.
Yeah. Because it's
right? Because I go back to the same graph, and now I'm like going from the right-hand side.
It'd be negative
and it's going to be negative infinity, which is still on top of infinity, right? Okay. Last example of the day. We save the best for last. The moment you get lost, you stop me. Okay? Go ahead, and you need probably an entire page for this one, or give yourself some room. We're going to do an integral from 0 to e squared
Ooh, I like this already.
of the natural log of x to the third power dx. Calc BC, let's have some fun.
Yeah.
Alright? Okay.
You made it e squared so that when you plug it in, it's easy to find it.
Exactly. So, I mean, we're dealing with natural logs, right? So, should be easy to get rid of later on.
There's
an asymptote at
Okay.
zero, yeah.
There's what?
Asymptote is 0.
Oh, there's an asymptote at 0. You guys agree?
Yeah.
Remember, you can't take the natural log of 0, therefore there's got to be an asymptote there. So from the beginning, we have a problem. What's the problem?
Yeah, but asymptote is
0. So right away, we know that this is improper. Yes? So because this is improper, I'm going to rewrite it as the limit as a approaches 0 from where? From the right of the integral between a and e squared. And to make my life easier, can I rewrite this as 3 natural log of x dx? Yes?
Oh, use a in place. Oh, yeah.
Sweet. Okay, now what? Now we integrate. Okay.
Which is just
How do I integrate ln x?
it's just 3 over x. Oh, no, it is
Ooh,
not
no,
3
it's
over
not, because the derivative of ln x is 1 over x. What's the integral of natural log of x? If you have it memorized. If not, integration by parts.
No.
Liotte.
Liotte.
I say we just take the shortcut.
Liotte. No, we're going to use Liotte. Stay with me. So, right away, what's u?
U equals ln x.
U equals the natural log of x. And right away, what's dv?
dv equals dx.
Can I go ahead and keep the 3 with that? So
No.
3 dx. It actually makes things a lot easier. Promise. So what's du? 1 over x dx. And what's v? 3x. Yes? Okay, so here's where I'm at. The limit as a approaches 0 from the right of, okay, we're going to go ahead and integrate this. So the integral of that Liotte, so it's u times v, right? So it's
3x ln x.
3x ln x minus
Reduce.
the integral of v du. So 3x times 1 over x dx. Now I'm showing more work than I expect you to show, but just to make sure I don't lose anyone. Now, this is still a definite integral, right? So from a to e squared, right? Yes? Okay. So then the limit as a approaches 0 from the right, 3x ln x. Doesn't this just become 3? What's the integral of 3?
3x.
So minus 3x from a to e squared. Yes? Now let's pause. So now you could memorize the integral of natural log of x. You could. But you don't have to. You have integration by parts. It really didn't take that long. It wasn't that bad. Okay? But anyways, here's where we're at. Now what? So let's first fundamental, right? So the fundamental. Alright. And if you're watching this video on the internet, that's heavily argued. Some people call it the first, some people call it the second. Just apply the fundamental theorem of calculus. Okay? So first we're gonna plug in what? E squared. So 3e squared natural log e squared minus 3e squared. And then what?
It's equal to 3x.
Minus, say that one more time.
It's the whole thing, not just the 3x?
It's the whole thing, because remember, this entire thing came from here. Right?
But then
You
what
with me?
happened to the smaller one?
What smaller one?
Like, the one from, like, what happened to this one? Because if you're taking that of that.
I mean, I didn't write it, guys, but look, technically, I mean, I could have written it here.
So then
I
that
just waited till
that
the
just
end.
goes away. Like this one is for the.
No, wait, it's not
No,
gonna
like,
be
look,
negative
right
minus
here,
4 and then it has
this right here, when you multiply 3x times 1 over x, that
It's
becomes
3.
3x over x, which becomes 3.
and then you integrate that.
The integral of 3 is 3x.
Okay.
So you basically
So
just
then I-
integrated f of x.
Okay, now, I plugged in the e squared, now I gotta plug in the a. Yes? Okay, don't let algebra stop you. Alright, what's the natural log of e squared?
2.
2. Be careful. So what's 2 times that?
60 squared minus 3 squared, which is 3 squared.
Good. And then there's nothing you can do here, so I'm just going to go ahead and distribute the negative. So minus 3a natural log of a plus 3a. Yes?
It's divergent.
Hold on. Stay with me. Stay with me. Okay. We're going to find limits. You ready? Stay with me. So please stay with me. Hold on. First plug in, right? If it works, we're good, right? I'm going to plug in 0 into, well, isn't this just a number? So so stay with me. So when it's just a number, it just approaches the number, right? So this is just 3 squared, right? Minus. Okay, if we plug in 0 there, we have a problem. We can't do that. So I'm going to pause for a moment. I'm like, okay, I can't take the way that it's written, I can't do it yet. So I'm going to write it as the limit as a approaches 0 from the right of 3a natural log of a. I'll take care of that later. Now I'm going to try it here. What's going to happen if you plug in 0? Plus 0. Okay. So for sure, I was able to at least get that, right? Now I got to solve that limit.
It's divergent.
Hold on, dude. Hold on.
Oh, you can put it back in.
Hold on, dude. Hold on. 3e squared minus the limit as a approaches 0 from the right. Okay, first of all, if I plug in 0 here, 3 times 0 is, so I get 0, right? Now, what happens as you approach 0 of a natural log graph?
Negative infinity.
You go to negative infinity. If you're not quite familiar, here's what the graph of natural log looks like. So as you're approaching 0, you are going to negative infinity. Now, if you did your L'Hopital's homework, you should recognize that this is a form of L'Hopital's rule. But I can't apply L'Hopital's the way it is. L'Hopital's needs to be indeterminate in the form of 0 over 0 or negative infinity over infinity, some type of infinity, right? The fact that I have something times infinity, it's indeterminate. But I need to manipulate this algebraically to make that happen. What's up?
Do 3 ln a over a to the negative 1.
So you're saying do 3 natural log of a over what?
Over a to the negative 1.
Okay, is that the same thing as from what it's above? Okay, let's plug in. If you plug in 0 here, you get some type of infinity, right? Because, right, as we approach 0, it goes to infinity, right? Now, if you're not quite seeing it, isn't a to the negative 1 the same thing as 1 over a? You with me? And once again, if I graph 1 over a, that's the same thing as 1 over x. What does the graph of 1 over x look like? Asymptote here, asymptote there, right? And then it looks like that. Yes? What happens as you approach 0 from the right-hand side? Infinity. Infinity over infinity means what? L'Hopital's rule. So, I still have this 3e squared minus the limit as a approaches 0 from the right-hand side, and I need to take the derivative of this. What's the derivative of 3 natural log of a? 3 over a. Yes? 3 over 8. All over What's the derivative of a to the negative 1 power?
That's also ln a.
No,
Or that's
derivative.
the integral.
Hold on, derivative. So negative a to the negative 2, right?
Negative one.
So that's negative 1 over a square. Okay, let's clean this up. So I have 3 over a times the reciprocal of this, which is a square over negative 1, right? So that goes away, leaving you with negative 3a. What's the limit as a approaches 0 of negative 3a?
0.
So what's the final answer?
3 squared.
3 squared. So did it diverge? No, it did not. It converged. Therefore, I'm going to go ahead and flip the page here in just a second. It converges to what?
3 squared.
So if we go back and you answer the question, I'm getting lazy and I don't want to waste another piece of paper. I'm going to say, therefore, the integral from 0 to e squared of natural log of x cubed dx is equal to what?
3e squared.
3e squared.
Wow.
And we're done. Alright, so for homework, make sure that you practice this, especially if you are struggling with the whole idea of asymptotes and right-sided limits, left-sided limits. Typically, let's be honest, a lot of those left-sided, right-sided limits, if you have an asymptote, it's going to be some sort of infinity, right? But anyways, that's all I got for you guys today.
Are we gonna eventually